Lesson 2, Equilibrium, Characteristics and Chateliers Principle. Part 1, Characteristics of Equilibrium. We're not going to go into the same amount of detail we did in class. This is just a general overview of the characteristics of a system in equilibrium. When a system is in equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That means the amount of products turning into reactants equals the amount of reactants turning into products. Equilibrium must occur in a closed system. Any stress on the system may cause the exchange amounts to change. This includes stuff like heat. So equilibrium only occurs at a constant temperature because all reactions have a delta H value. So heat is either a reactant or a product in any reaction. Equilibrium can be established from either side of the chemical reaction, products or reactants. In lesson 1, we did the whole entire exercise twice. We started with all the water in fish tank A. Second time, we started with all the water in fish tank B. Given time, we saw that both times we conducted the experiment, we wound up with the exact same end result. The system eventually found equilibrium. So whether starting with products or reactants, a system will find equilibrium. Equilibrium is dynamic, meaning the reaction is always taking place, even though it appears nothing is happening. We know that there's an exchange happening between the products and reactants. But why do we not see anything changing? And that's because equilibrium must exhibit constant macroscopic, that's those visible properties. So the color, volume, pressure, and concentration cannot be changing. And that makes sense because if the amount of products aren't changing and the amount of reactants aren't changing in their total amount, then we won't see any change. If they aren't in equilibrium, then that means that we have a shift. So products are going up and reactants are going down, or vice versa. Which means, well, if we look at something like color, if the color is changing and the color that we see is getting darker and darker, that means that the system is not in equilibrium. That means that it's still shifting. And not until we see constant macroscopic properties, the system will not be considered to be in equilibrium. Part 2, Chateliers Principle. Any change to a system in equilibrium may result in destabilizing the system. In this event, the equilibrium will shift in an attempt to lessen the effect that has caused the destabilization. So what does this mean when we're doing Le Chatelier principle questions and we want to know, does it shift left or right, or is there no shift? Well, it's best to think of Le Chatelier as a grumpy old man. Whatever you try to do to the system will shift to work against what you are trying to do. I'm trying to increase pressure. No, I'm going to decrease pressure. I want to increase the temperature. No, I'm going to decrease temperature. Always fighting you every step of the way. Important to remember as we go through this, and we'll talk about this more later in the lesson, but all shifts in equilibrium occur due to changes in either concentration or temperature. So here we have a system in equilibrium. Now there's no true reactants or products because the reaction is going both ways at the same time. So both sides are actually reactants and both sides are actually products. But when we refer to a system in equilibrium, whatever we put on the left-hand side we call reactants, and whatever we have on the right-hand side we refer to as the products. Now when in equilibrium, the amount of products turning into reactants equals the amount of reactants that are being turned into products. That's what makes it equilibrium. The exchange is equal. A shift in equilibrium means that the exchange between products and reactants is not equal any longer. A shift to the left means the amount of reactants will have increased and the amount of products will have decreased when the new equilibrium has been established. Given time, the system will reach a new equilibrium and there will be more reactants than there were prior to the shift, and there will be fewer products than there were prior to the shift. Now, if we have a shift to the right means the amount of reactants will have decreased and the amount of products will have increased when the new equilibrium has been established. And again, given time, the system will reach a new equilibrium, so the exchange again will be equal, but when we reach that new equilibrium, there will be fewer reactants than there were prior to the shift, and there will be more products than there were prior to the shift. So again, to recap, a shift in equilibrium means that the exchange between products and reactants is not equal any longer. If given enough time, the shifting system will find a new equilibrium. That means the exchange between products and reactants will become equal again. The amount of reactants will no longer be changing. The amount of products will no longer be changing. The amount of reactants will be different from what was present before the shift, and the amount of products will be different from what was present before the shift. Things to keep in mind as you work through the assignment. Now remember, we said equilibrium only shifts when there's a change in concentration or in temperature. Now solids and liquids do not have concentrations, so the addition or removal of either will not cause a shift in equilibrium. Noble gases do not interact with other molecules. When added to the system, they float past other gas molecules undetected, and they also will not cause a shift in equilibrium. And lastly, a catalyst will not cause a shift in equilibrium. It will speed up the reaction in both directions. Now, if you remember back to grade 10, there was talk about catalysts, and a catalyst is something that speeds up a reaction and is not destroyed in the reaction. But since this reaction goes both ways at the same time, not only does it speed up the forward reaction, it also speeds up the reverse reaction. And the net effect is we don't see any change in the amount of products or reactants. The exchange happens quicker, but the amount of products and reactants do not change in their amount. So let's start off with this reaction. Carbon dioxide and hydrogen react with heat to make carbon monoxide and water. Now let's say we add heat to the system. That means I'm trying to heat the system up. I'm trying to warm it up. So that means the system's going to try to cool it down, because it always does the opposite of what I'm trying to do. And in order to cool it down, it's going to shift to the right. Because when it shifts to the right, it's going to make more carbon monoxide and water. And at the same time, it's going to use up carbon dioxide, hydrogen, and heat. So the carbon dioxide, hydrogen, and heat will decrease with a shift to the right. So a shift to the right, that will allow it to decrease heat. So now we try to take out carbon dioxide. If I try to decrease the amount of carbon dioxide, the system's going to try to increase the amount of carbon dioxide. So to increase carbon dioxide, we want more stuff on the reactant side, so it's going to shift to the left to produce more of what's on the left-hand side, which includes carbon dioxide. So we add N2. N2 is a gas, and I'm adding it to the reaction vessel. So what am I trying to do? It's not in the equation anywhere. If I add gas to a reaction vessel, it's like adding gas to my tire. And when I increase the amount of gas in my tire, I've increased the pressure, the PSI of the tire on my car. So if I'm adding N2 to this system, a closed system, it is going to increase the pressure inside of that reaction chamber. And if I'm trying to increase pressure, the system is then going to try to decrease pressure. And how is it going to do that? Well, to increase pressure, I could add gas. So in order for the reaction to decrease pressure, it is going to want to decrease the amount of gas. And if I look at the equation, on the left-hand side, I have a carbon dioxide and 2 hydrogen gas molecules. So that's a total of 3 gas molecules on the left-hand side. On the right-hand side, I have 2 water molecules, which are liquids, and only 1 gas molecule, which is the carbon monoxide gas molecule. So if it wants to decrease pressure, it can make a carbon dioxide and 2 hydrogens come together, and the result is it forms 1 carbon monoxide gas molecule and 2 liquids. So there would be a shift to the right, a shift to the side with fewer gas molecules. All right, so now we add argon gas. And if I add argon gas, I am trying to, hold on a sec. Argon is a noble gas. See? It's right here on the periodic table. And like we said, noble gases mean no shift. That one was easy. Let's try to double the size of the container. Double the size of the container. What does that even mean? Well, let's try to imagine, if we will, a gas that is being compressed by two pistons. It is squeezing the gas together. And if we double the size of the container, that's like us pulling the pistons out partially, which will then, well, that means there'd be less pressure. So that means if I double the size of the container, I'm trying to decrease pressure. And if I try to decrease pressure, the system's going to try to increase pressure. And we already established that there are three gas molecules on the left, there's one gas molecule on the right, so if it wants to increase pressure, it is going to shift to the left so there are more gas molecules, increasing the pressure. So we add a catalyst, and a catalyst speeds up a reaction. And a catalyst will speed up both the forward and reverse reaction. And we said that since it's speeding up the forward and the reverse, well, the exchange just happens quicker, but still an equal exchange, which means there is no shift. So I'm adding chlorine gas. It's not a noble gas, and it's not in our equation. So that means if I'm adding a gas, I'm just trying to increase pressure. So that means the system's going to try to decrease pressure. And to decrease pressure, it will then want less gas. And in this equation, I have two gases on the left-hand side with the two ammonium molecules. And on the right-hand side, I have one nitrogen and three hydrogen molecules that are gases, so four gases on the right. So to decrease pressure, it wants less gas. It will shift to the side with less gas, so that means we're shifting to the left. Now we're going to remove ammonia. Ammonia is NH3, so I try to decrease the NH3, so therefore the system will try to increase NH3. So to increase NH3, it's going to want to make more of what's on the left-hand side, so it's going to shift left. Add a catalyst. Again, like we said, a catalyst will speed up both the forward and reverse reaction. There is no shift. Half the volume of the container. Well, let's bring those pistons back in here. And if we're having the size of the container, those pistons are going to squeeze that gas together. So that means I am trying to increase the pressure. And the system will then try to decrease pressure. And in order to decrease pressure, it will shift to the side with less gas. Again, less gas means less pressure. So if I look at the equation, we have two gases on the left-hand side. There are four gases on the right-hand side. To decrease pressure, it's shifting to the side with less gas, which is then a shift to the left. Add carbon dioxide gas. CO2 is not in the equation. It's also not a noble gas. So if I am adding a gas that is not a noble gas or in my equation, that means I'm trying to increase the pressure. So the system will try to decrease the pressure by going to the side with fewer gas molecules. Again, in our equation, there are two gases on the left, there are four on the right. So to decrease pressure, it is going to shift to the left, the side with fewer gas molecules. Now I add O2. O2 gas, and O2 gas is in the equation. So if I'm trying to increase the O2 gas, the system will try to decrease the O2 gas. It's going to decrease the O2 by shifting away from it. So it's going to shift to the left. Now I'm going to add calcium carbonate. So I try to increase the calcium carbonate. The system will not shift because it's a solid. You cool the system down. So you try to take the heat down. It's going to try to push the heat up. And to increase heat is then going to shift to the side with heat to push it up, which means we're shifting to the left. Remove calcium carbonate. You try to remove calcium carbonate, so decrease it. So the system's going to, again, I don't know if I got you this time, no shift because it's a solid. You add carbon dioxide. Carbon dioxide is not in the formula. It's also not a noble gas, so that means we're trying to increase the pressure. And if we try to increase pressure, the system's going to try to decrease pressure. We have no gases on the left-hand side. There's only one gas on the right-hand side. So to decrease pressure, it will shift to the side with fewer gases. So that means we're looking at a shift to the left. Now make a note to yourself that a change in pressure will result in no shift if there are an equal number of gases on either side. This is because it cannot shift to a side with more or fewer gases. I would be remiss if I did not mention this before you go on to the assignment, for this will appear in the assignment. It will probably appear on the unit test, maybe the final, probably on a quiz. The delta H. So if I'm given the reaction and the delta H value is given separately. Remember, from last year, a positive delta H value means the reaction is endothermic, which means heat is entering the reaction. So those kilojoules, that heat goes on the left-hand side because it's going into the reaction. If the delta H value is negative, that means the system is exothermic and heat is exiting the system. In which case, the heat, the number of kilojoules, will go on the product side because the heat is leaving the system, it is exiting. Now let's put that into practice. The delta H is positive 32 kilojoules. That means the reaction is endothermic and heat goes on the left-hand side. It enters the reaction. So I write the 32 kilojoules on the left-hand side. I'm trying to cool the system down, so it is going to try to heat it up. And it's going to do that by shifting to the left, increasing everything that is on the left-hand side, including the heat. That's the end of the lesson. You're good to start working on the EQ1 assignment.